All right, guys, quiz should be timing out for pretty much everybody at this point. I was tracking it as you were taking it, and I'm glad to say it looked like you guys were doing pretty well with this one. So good job. I think you're sort of getting the gas laws nicely. I have noticed a little bit of a fall off on the 5 for 5 quizzes. I just say be careful there because they do tend to add up. So don't ignore those. Those are usually fairly quick, easy pickups of small number of points. So make sure you're paying attention to those and not skipping them or not preparing for them, because that is a good, easy way to pick up points. So don't forget about those. One other announcement I need to make is that you won't have class on Monday. You get the day off because I get my COVID shot on Monday right about the time class is happening, and I didn't want to delay that appointment. So you guys get a day off. So we'll reconvene on Wednesday and we'll have a normal 5 for 5. And go ahead and look at the next video, which actually introduces us into the next topic, which is going to be thermochemistry. So we'll see you on Wednesday and not Monday. So make note of that. If you show up, the Zoom meeting will be there, but I won't be there. All right, so what did I want to do today is to finish up with the gas laws at this point. So we've pretty much talked about all the different gas laws that we can talk about, but now we want to delve a little bit more into the theory. All right, and then when we're done with that, we'll go back and do some practice with Chem 101. And the practice will deal with what we dealt with in the video, which is eudiometry, and we're going to throw a little gas law stoichiometry in there as well, where we'll use mole bridges within the context of the gas laws. You guys actually had a quiz question on that, and most of you look like you were doing pretty well with it. All right, so I want to talk a little bit about the actual theory of gases. So when we talk about the behavior of gases, especially the pressure relationships, what we're really talking about is something called kinetic molecular theory. So it's essentially going to be a simple theory that's going to let us explain the simple gas laws. Okay, so those are things like Boyle's law and Charles's law and Avogadro's law. And of course, all those things combine to give us the ideal gas equation. So we're going to have a few assumptions about a gas. And the theory is really based on these simple assumptions. All right, so the first assumption about any gas that we're going to make is that the gas itself is going to be comprised of moving particles. My wife just got back. She got her COVID shot today. And the assumption is that the particles are spaced far apart. Okay, so keep in mind, if we're talking about a liquid or a solid, the particles are still there, but they're close together. But in the case of a gas, as you guys know, the particles are very, very far apart. All right, now that's important because when we get to the next assumption, that assumption is that the particles are so far apart that they don't even recognize each other. In other words, there are no attractive or repulsive interactions between the particles. So for example, if I have something that's more condensed, like a liquid or a solid, and the particles are close to each other, then they feel each other, right? They can actually attract each other or repel each other. But in the case of a gas, those particles are so far apart that they never even sense those kinds of interactions. And this is the assumption that we make when we talk about an ideal gas as opposed to a real gas, okay? So you might wonder, when we talk about an ideal gas or the ideal gas equation, what are we really saying there? Well, we say that the gas behaves ideally, and what that means is that the particles are so far apart that they just don't interact with each other in any meaningful way. Okay, so that's the definition of an ideal gas. So that's why I'm putting it there. The third point we want to say is that pressure comes about or results from collisions between the particles and the wall of the container. All right. Remember, that goes back to our very first discussion of this. I think we talked about a video where we talked about, for example, how pressure is really sort of comes from the force of a particle hitting something, right? So we talked about that. And then the last thing, which is important, is sort of the temperature relationship. If we have a moving particle, that particle is going to have kinetic energy associated with it. And we'll come back down and redefine kinetic energy here in just a moment. But basically, what we can say about our grouping or ensemble of particles is that the average kinetic energy of the particles is going to be proportional to temperature. So all I'm saying here is that as the temperature of the collection of particles goes up, the particles are going to move faster. And when they move faster, they gain more kinetic energy. Okay. So when we talk about kinetic energy, here it is. Kinetic energy is equal to 1/2 the mass of the particle times the square of its velocity. So m here is the particle mass, and v here is the velocity or the speed of the particle. All right. So mass might be, for example, in terms of grams, and speed might be in terms of something like meters per second or something like that. All right. So that's how we define the kinetic energy of the particle. So again, you can see there's a temperature dependence here, right? Not through the mass, but through the speed or velocity of the particle. In other words, as the temperature goes up, the particles move faster. If they move faster, obviously they have more kinetic energy. There's a squared relationship there. Okay, so everybody okay with this so far? So let's take these assumptions that we just made and let's sort of talk about pressure. Okay, so when we talk about pressure, pressure is going to be a function of several things. It's going to depend on several things. Okay, the first one is going to be the total number of collisions against the container wall, right? The more collisions we have, the higher the pressure. Now, let's think about this in terms of what this is a function of, because what variables do we have to play with, right? When we talk about pressure, what are our variables? When we go back to the gas laws, we got volume, we got temperature, and we got number of moles. So do all of those things actually dictate or control to some degree the total number of collisions between the particles and the container walls? Does the temperature dictate that? So in other words, what is all this going to be a function? What's going to be a function of temperature, the volume, and N, the number of moles of the gas. So let's think about that for a second. Why would the total number of collisions be a function of temperature? Anybody want to explain that? Think about how that just might work. If I jack up the temperature, why would I get more collisions? So what happens to the particles when I increase the temperature?
Will they move faster?
Yeah, they're going to move faster. That's exactly right. They get more kinetic energy, so that means they move faster. So think about it. If I put all of you guys in a single room, we don't have COVID, right? Put you guys all in a classroom and blindfold you, right? and I tell you to sort of randomly walk around, eventually you're all going to bump into the wall, right? That's pressure. But if I blindfold you and then tell you to run, okay, is that going to increase or decrease the frequency with which you're going to bump into the wall if you're moving faster? What do you guys think? Yeah, it's going to increase it. You're going to have more collisions. Yeah, exactly. You're going to increase because, the faster you're moving, the more likelihood you have of bumping into something, right? So pressure is definitely a function of temperature. How about volume? What if I made the room bigger? Would you increase or decrease your chance of running into the wall?
Decrease.
Decrease it. But if I made the room smaller, what would happen? Would you increase or decrease your probability of running into the wall?
Increase.
Yeah, exactly. So volume definitely makes a difference. How about N? That's the number of particles in the ensemble. What if I had 2 people in the room versus 50 people in the room? If I have 50 people in the room, what's going to happen to the frequency of collision? It's going to go up or go down. Yeah, it's going to increase. So yeah, the number of moles of particles matters. Okay. So you can see the total number of collisions between the particles in the wall are going to be a function of all of those variables. That's pressure, right? The second thing is that we have to concern ourselves with the energy per collision, right? So if you think about it, if you have a particle hitting the wall of the container with a small kinetic energy, is it going to impart a lot of force to the wall? Probably not. But if I have a really fast moving particle and it hits the wall, it's going to impart more kinetic energy to the wall, right? So the energy per collision matters. And it matters through the velocity, right? And the velocity depends on the kinetic energy. So when I get into this, this is going to be a function of the kinetic energy of the particle, which in turn is a function of the velocity. Okay. Now, what does the velocity depend upon? Well, the velocity depends in turn on the temperature, as we just stated. Okay, so again, as the temperature goes up, the particles move faster. As the particles move faster, they gain more kinetic energy through the equation I just showed you above. And when I have a collision between a high kinetic energy particle and the wall, more energy is going to get transferred to the wall. That means the pressure goes up. Okay, does that make sense to everybody? All right, so what we want to do is look a little more closely at this temperature dependence, because that's important. So when we talk about the temperature dependence, the way to do this is through something called the Maxwell distribution. And what the Maxwell distribution does for us is it lets us plot a graph of the number of particles with a given velocity or speed as a function of the actual velocity, okay? So it's really kind of a distribution. So what we find is when we have an ensemble of particles, a big collection of them, they don't all move at the same speed or velocity. Okay, so essentially what I have is something that looks like what we might call a normal distribution, which is kind of the Brontosaurus curve, right? And it looks something like that. Okay, so basically at a given temperature, I can say that I have an average velocity, and that would be corresponding to the top of the curve, right? So at that point, that would be my V average for my particles. But keeping in mind, since I have a big collection of particles, some are going to be moving more slowly, some are going to be moving faster. So the ones that are to the right of the dashed line there are faster moving than the average. And then I should have a somewhat equal number that move more slowly. And those are to the left of the line. Okay, but the point is you get a distribution of velocities here. And basically the area under the curve has to represent the total number of particles that we have in the ensemble. So now the question becomes, what happens to this curve if I vary the temperature? So I can say, for example, this would be T1. That's for a specific temperature that I have. Now, what would happen now if I increase the temperature where T2 is greater than T1? So what do you think the average velocity is going to do? Go up, go down, or stay the same if I increase the temperature?
Go up.
It's going to go up,
Increase.
okay? And then the other thing that's going to happen is the curve is going to broaden out, okay? So what we'll find is it's still a normal curve. It still has the same area as the other one because that's defined by the total number of particles, but it broadens out and moves to a higher temperature. So now what I might get is something that looks like that. Okay, so the curve isn't as tall, but it's more spread out. So this would be at T2. Okay, so now if you take a look at this, this would be my V average at T2. So the point is, as the temperature goes up, the average velocity of the particles also increases, but I have a distribution of velocities. So that's the important thing to remember about the Maxwell distribution. So now you're in a position where we know enough to be able to start talking about the individual gas laws. Okay, so could we use the kinetic molecular theory now to talk about, for example, why pressure is proportional to 1 over volume? That's Boyle's law. What's held constant here? That's at constant N, number of moles, and temperature, right? So this is the one where we talk about decreasing the volume of the room, right? So if the room gets smaller, we're going to get more collisions, right? Now the energy of the collision isn't affected, but I'm just getting more collisions as I make the room smaller. So what's going to happen to the pressure? It's going to go up. Okay, so we can use kinetic molecular theory to explain that now. What if I wanted to go to Charles's law, where I say that pressure is proportional to temperature at constant N and V? So now I'm holding the number of particles constant and I'm holding the volume of the room or the container constant, but I'm jacking up the temperature. What's going to happen to the pressure? Oh yeah, it's proportional. It's going to go up. Why? Oh, well, this is the argument we made about the particles moving faster because they have a higher kinetic energy because of their higher velocity, right, at a higher temperature. So this means now that we're going to get more collisions and the energy per collision is also going to increase. So that proportionality makes sense. So now what about Avogadro's law, where pressure is proportional to N, and now what's constant? We're at constant, let's see, V and T, right? So the room's the same size, temperature is held constant, but now I'm putting twice as many people or particles in the room. What happens there? Well, the energy per collision doesn't increase, but the total number of collisions increases because I've got a larger number of particles in there. So I have a higher frequency of collision. All right, so see how I can kind of take those ideas from kinetic molecular theory and now sort of explain what's happening in these simple gas laws based on what those particles in the gas ensemble are actually doing. So it's really a nice little model, and it's a good example of a model that we can use to explain something that we can't directly see, but sort of extrapolate based on the behavior of these particles. All right, any questions about that, guys? All right, so let's practice a little bit. So I want to sort of get into some of the video stuff here. So this is where we can do a little udiometry and a little bit of gas law stoichiometry. So I have a few problems here for us to work. Let's hop right there to it. And let's start it. Okay, so we're active here. So see how far you guys get. So for example, that first problem is going to look a whole lot like the example problem we did in the video. Number 2 is a good one. So I say if you get 2 done, try doing 1 and 2. As you can tell, the trick with all these problems is basically getting everything in terms of moles so you can establish a mole bridge.
Can you go over number 1?
Sure. Let's see here. Do a setup here, if you like. Okay, so for number 1, what have we got? So it says how many liters of hydrogen gas would be produced by a complete reaction of 2.93 grams of aluminum. So I'm just going to write these down as I go.
I can't see your screen. I don't know if that's on me or what.
Yeah, I can't see.
Can anybody else see it? Let me see. I might have to go back. So I might have to go back and share again. Let's see what happened. I wonder if I lost I wonder if I lost internet there for a second and I lost my screen share. Here we go. Yeah, I did lose it. That's the first that's happened. Sometimes the internet will skip here and I'll lose my screen share. Okay, let's go back. There we go. Thank you. 2.93 grams of aluminum. Okay, and I'm at STP, right? So if I'm at STP, that's kind of nice because I can make a direct movement between liters and moles, right? But the first thing I got to do is get to moles. So I've got the aluminum, so I need a mole ratio, or rather a way to get from grams of aluminum to moles of aluminum. So I know that 1 mole of aluminum. Anybody got their periodic table handy? You know what the mass of aluminum is?
It's 26.98 though.
It probably says it in the problem. All right, there we go. So grams of aluminum. So now I can establish a mole bridge, can't I? So I want to relate aluminum. So how many moles of aluminum do I have in there? It looks like 2 moles of aluminum in the balanced equation, right? That goes in the bottom. And I want to relate that to what the hydrogen gas I'm making. Yeah. So it looks like I got 3 moles of H2. Does that seem right? Just using my mole bridge in the balanced equation. And that gets me to moles of hydrogen, but I want volume of hydrogen, don't I? But I'm at STP, so I have a direct way of getting there without having to go through the ideal gas equation, don't I? I know that for every 1 mole of a gas, which is hydrogen in this case, I've got what, 22.4 liters of it? So that should give me the liters of hydrogen gas that I need. So that looks like the setup that we need. Does that look like it works? We'll just make sure grams of aluminum cancel with grams of aluminum, moles with moles, moles hydrogen with moles hydrogen. We're left with liters hydrogen. That should do it.
Okay, that makes sense. Thank you.
Yeah, and number 2 is very similar to that. It's just you have to do a few more conversions up front, but it's basically the same problem. You're starting out with 60 liters of gasoline. You got to get that from liters to grams, or kilograms rather, kilograms to grams, grams to moles, then use your mole bridge. And then you're not at STP anymore. So once you have the moles of your CO2 gas, then you got to use PV equals nRT to get back to the volume because you're not under standard conditions anymore. It's basically the same thing. You still got to get to moles and then work from moles through the ideal gas equation back to volume. See how people are doing with that one. I'm kind of curious. Yeah, people are getting there. See if anybody's gotten to 3. Yeah, somebody got to 3. That's good. 3 is a straight up udiometry problem like we did in the video. Yep, a couple more have gotten the last problem. That's good. It's interesting. You see how in chemistry, everything comes back to those mole bridges in the equations, right? That's something we never seem to get away from. So in the last minute or two here, guys, feel free to keep working. You've got like almost 9 minutes left on this if you want to use it. But just a quick reminder, you get the day off on Monday, guys. So if you show up, I won't be here. So again, remember that we'll meet on Wednesday and I'll try to open up the problems, the homework problems for the next chapter so you guys can start working on those if you want. And we will start into thermochemistry. So make sure you're watching the next video, which is an intro to thermochemistry then. All right, any other questions, guys? All right, well, everybody have a good weekend. It's beautiful out there today. So if you can get outside, make sure you go get outside.